Hi everybody, this is Dave Moraine again. This is part 3 of our series of videos trying to derive the probability that two randomly chosen positive integers will be relatively prime. The first two videos set it up, gave you the background, the needed definitions, and our goal is to prove that this probability is roughly 60%, 6 over pi squared, the reciprocal of pi squared over 6, which we derived previously. We got up to the point where we were able to express the probability as a product of factors, in fact, a product that never ends, an infinite product, as it's called. And quickly review. 1 over 2 squared is the probability that m and n are both divisible by the prime 2. We subtract from 1, which means m and n are not both divisible by the same prime 2. The next factor is the probability that m and n are not both divisible by the same prime 3, not both divisible by 5, not both divisible by 7, and so on. So these factors all have primes in them. And somehow we have to transform this product into something that looks like this. And that's the magic of mathematics, if you will. I don't see it as magic, but that's what math is all about, changing form. If I just took the first two factors and multiplied it out by distributing, we would get 1 minus 1 over 3 squared minus 1 over 2 squared plus 1 over 6 squared. 2 squared times 3 squared is 6 squared. Remember this simple basic property of arithmetic and exponents is what is going to enable us to get every single denominator here. But unfortunately, this is not working out for us because we are not getting the positives we want. We want a sum of these fractions. So this is where we have to be very creative. Now, looking at this, you might say it doesn't remind you of anything, but those of you who recognize the formula for the sum of an infinite geometric series may recall that the sum of an infinite geometric series is a over 1 minus r. Well, the 1 minus r is right here, and a is 1. So we're going to play a little game to transform each of these factors into something that looks like an infinite geometric series. Now, if you don't have the background in what I just said, that will make no sense. So I'll slow it down a little bit. We're going to exploit a basic algebraic property that any non-zero number is equal to the reciprocal of itself, a double reciprocal. And we could write this using negative exponents. Remember I told you one of the prerequisites was good algebra skill. So putting all this together, we're going to write the first factor as the reciprocal of 1 minus 1 over 2 squared. And the next factor, the reciprocal of 1 minus 1 over 3 squared. And that got a little bit too big. And then this will be, again, a double reciprocal, 1 over 1 minus 1 over 5 squared, etc. Each of these factors in the parentheses is fits the formula for the sum of an infinite geometric series. For example, a is 1, r is 1/4, or 1 over 2 squared. Then this formula, a over 1 minus r, gives us a value for the sum of the following infinite geometric series, which you should recognize, or you will, as you get into Algebra 2 and pre-calculus, except in our problem, a is 1, r will be 1 over 2 squared, or 1/4, so it's 1 plus, all the a's are 1 here, 1 over 2 squared to the first power. first power, plus 1 over 2 squared to the second power, plus 1 over 2 squared to the third power, and so on. That's the background you need. If this doesn't make sense, you're going to have to accept it formally, and because of the time constraints, I'm now going to rewrite this. So we have our negative reciprocal outside, and this is 1 plus 1 over 2 squared to the first power, 1 over 2 squared to the second power, plus 1 over 2 squared to the third power, running out of room and time. Okay, the next one, I'll try to leave more room for this one. A1 plus, and this time our R value is 1 over 3 squared to the first power. I'm writing it bigger. 1 over 3 squared to the second power, plus 1 over 3 squared to the third power, etc. And don't forget, each of these is raised to the negative 1, but we're not going to worry about that negative 1, as you will see. And we'll do one more just for practice. 1 over 5 squared to the first power, plus 1 over 5 squared to the second power, etc., all raised to the negative 1. Now, how in the world are we going to turn this into this sum? The reciprocal is there for us. That's what's going to flip it over. But how do you multiply all this out? Well, this applies to any infinite process when I'm explaining it at an elementary level. I'm not using heavy symbolism. I'm not worrying about convergence and the theorems of advanced mathematics. I'm just doing it formally, just as Euler might have done. So how would we multiply this out? Well, we could certainly multiply 1 times 1 times 1, the first term of every factor, or of every sum. So that will give us 1. And then we'll have 1 over 2 squared times 1 times 1 times 1 times 1. That's 1 over 2 squared. We're getting there. Then we'll have 1 over 3 squared from here, multiplied by 1 times 1 times 1, and so on. What about 4 squared? Where's 4 squared? Well, 4 can be factored as 2 squared, and that's the key to this. Even though 4 is not a prime number, it's 2 squared squared, which is right here. We're not going to miss anything, are we? 1 over 5 squared, that's a prime. We got that one covered. What about 1 over 6 squared? Remember I told you to look for that before? Remember it, rather. That's 1 over 2 squared times, oops, went too far. 1 over 3 squared. Again, 1 over 2 squared times 1 over 3 squared. Oh, you got to know it. Plus 1 over 7 squared plus 1 over 8 squared. Well, how is 1 over 8 squared obtained? That's right, 8 is a power of 2. That's 2 to the third squared, or 2 squared cubed. So it's the same as 1 over 2 squared cubed, and we got that one. Similarly, 1 over 9 squared. 9 is 3 squared, so it's 1 over 3 squared squared. We got that one covered. 1 over 10 squared. That's 2 squared times 5 squared. We got that one covered, and so on. And the whole thing is raised to the negative 1. What's inside the parentheses, of course, is our pi squared over 6 raised to the negative 1. How do you like that? Now, of course, we are using properties extended to infinite sums and products. We're using the fact that the product of the reciprocals is the same as the reciprocal of the product. So we can take all of these factors and put them inside one large parentheses and raise it to the negative 1. All of this is pi squared over 6, so we arrive at 6 over pi squared. Well, I hope you enjoyed that. I mean, I just find this one to be one of the most gratifying derivations. I enjoy it. I love it. And I'm sure you could find others that are equally interesting. Please suggest that. In the last few seconds, again, I want to invite you to Math Notations, our blog, as well as come back, become a subscriber, add comments, any response you want to these videos so that I know you're enjoying them. Thank you.